Welcome to our study of the digestive system. Today, we are going to explore the fascinating world of associated digestive glands. Imagine trying to clean a very greasy frying pan after a heavy meal using only cold water. It simply does not work. You need dish soap to break down that stubborn grease. In this lecture, we will discover how your body uses its own biological detergents and chemical factories to make digestion possible. Let us dive in. Building on that dish soap analogy, your stomach and intestines act very much like a biological washing machine. But a washing machine alone cannot clean clothes without detergent. Similarly, your gut desperately needs biological detergents and chemical scissors to break down the complex foods you eat. The associated digestive glands are exactly these soap dispensers and chemical factories. They sit just outside the main gut tube, squirting in the necessary fluids at exactly the right time to make chemical digestion possible. Without them, the mechanical churning of the stomach would be largely ineffective against heavy fats and tough proteins. Now that we understand their purpose, let us formally define what these glands are. In comparative anatomy, associated digestive glands are specialized exocrine organs. The term exocrine simply means they secrete their products into tubes or ducts, rather than directly into the bloodstream. These ducts empty right into the main alimentary canal. The major players here include the salivary glands in your mouth, the massive liver, the gallbladder, which stores bile, and the pancreas. Interestingly, during embryological development, each of these organs starts as a tiny bud growing outward from the primitive gut tube. Even as they grow large and sit in the body cavity, they remain forever tethered to the digestive tract by their ducts. You might be wondering, why does the body bother building these separate, bulky organs instead of just letting the stomach and intestines do all the work? The answer lies deep in the evolutionary history of vertebrates. As early vertebrates evolved to become larger, faster, and much more active, their simple, straight gut tubes could no longer extract nutrients fast enough to fuel their demanding bodies. By outsourcing the heavy duty production of digestive enzymes and bile to specialized external factories like the liver and pancreas, the gut tube itself could become highly specialized for just absorbing nutrients. Without this evolutionary innovation, complex foods would pass right through undigested, leading to severe malnutrition regardless of how much food was consumed. This evolutionary specialization brings us to a critical process called emulsification. To truly appreciate how these glands work, we must look at how the liver's bile helps break down fats. The liver produces bile, which acts exactly like the dish soap we mentioned earlier. When you eat a fatty meal, the fat forms giant, unmanageable drops in your intestine. Emulsification takes one giant drop of fat and shatters it into hundreds or thousands of microscopic droplets. The entire goal of this process is to drastically increase the total surface area of the fat. By creating more surface area, the digestive enzymes from the pancreas have much more room to attack and break down the molecules efficiently. Now that we know emulsification increases surface area, let us look at the mathematics behind it. We can calculate this massive increase using the geometric formula for the surface area of spheres. The formula is A total equals n times 4 pi r squared. Here, A total represents the total combined surface area of all the newly formed tiny fat droplets. The symbol n stands for the total number of these small droplets. The mathematical constant pi is approximately 3.14159, And the variable r represents the radius of one of the new tiny droplets. This formula tells us that to find the total working space for our enzymes, we calculate the surface area of one tiny droplet and multiply it by the total number of droplets. As the radius decreases, the number of droplets increases exponentially, causing the total surface area to skyrocket. Before we calculate the total area, let us see this formula in action for just a single droplet. We are given a tiny fat droplet with a radius of 1 micrometer, which is the size created by bile salts. We want to find its individual surface area. We choose the standard sphere surface area formula because fat droplets form perfect spheres in the gut. We substitute our known radius of 1 into the equation. Squaring 1 simply gives us 1, leaving us with a final answer of 4 pi square micrometers. Physically, this represents the microscopic workspace available on just one single droplet for the pancreatic enzymes to attach and begin chemical digestion. To find the total surface area, we first need to know exactly how many tiny droplets are created from one large drop. This comes from the principle of conservation of volume. The total volume of fat does not change, it just gets divided up. By dividing the volume of the large sphere by the volume of a small sphere, the geometric constants cancel out, leaving us with this beautifully simple fraction. N equals capital R cubed divided by lowercase r cubed. The variable n is the number of small droplets. Capital R is the initial radius of the large fat droplet, and lowercase r is the radius of the new small droplet. If the small radius r decreases, the number of droplets n grows incredibly fast because we are dividing by a cubed number. Let us apply this droplet count formula to a real biological scenario. Imagine a single large fat droplet sitting in the intestine with an initial radius of 10 micrometers. The liver secretes bile salts that shatter it into uniform droplets, each with a tiny radius of 1 micrometer. We want to calculate exactly how many small droplets are formed. We choose our volume ratio formula because it directly connects the initial and final radii to the droplet count. We substitute capital R with 10 and lowercase r with 1. Cubing 10 gives us 1,000, and cubing 1 gives us 1. Dividing these gives a final answer of 1,000. This means the liver's bile has successfully shattered one single fat drop into exactly 1,000 microscopic pieces, perfectly prepped for digestion. Now that we know one drop becomes 1,000, we need to know how much the total surface area actually increased. We use a surface area multiplier called S. The formula is S equals capital R divided by lowercase r. Conceptually, this multiplier represents the ratio of the new total surface area to the old surface area. The symbol S is the multiplier itself, which has no units. Capital R is the large initial radius, and lowercase r is the small final radius. This elegant formula tells us that the increase in surface area is directly proportional to how much the radius is reduced. If the bile breaks the fat into even smaller droplets, decreasing lowercase r, the multiplier S will increase, giving enzymes even more space to work. Let us calculate this multiplier using our previous numbers. We are given the same initial large radius of 10 micrometers and the final small radius of 1 micrometer. We want to find the surface area multiplier to see exactly how much the bile helped the digestive process. We choose the multiplier formula because it gives us a direct comparison between the before and after states. We substitute capital R with 10 and lowercase r with 1. Dividing 10 by 1 gives us a final answer of 10. In practical terms, this means the liver's bile has just given the pancreatic enzymes 10 times more surface area to work on. This speeds up digestion by a massive factor of 10, showcasing the incredible power of associated glands. Now that we have used this formula and seen its power, let us understand where it comes from. We're going to derive the surface area multiplier formula. We start by defining what the multiplier S actually is. It is the ratio of the new total surface area to the initial surface area. We write this mathematically as S equals A total divided by A initial. Next, we substitute the geometric formulas for these areas. The new area is n times 4 pi lowercase r squared, and the old area is 4 pi capital R squared. Because 4 pi is a constant on both the top and bottom, we can cancel it out. This mathematical reasoning simplifies our equation, setting us up perfectly to substitute our droplet count in the next step. Continuing with our derivation, we now bring in the droplet count formula we learned earlier, where n equals capital R cubed over lowercase r cubed. We substitute this expression for n into our simplified surface area ratio. This gives us capital R cubed over lowercase r cubed, multiplied by lowercase r squared over capital R squared. To make the algebra clear, we group the similar variables together. We divide capital R cubed by capital R squared, which simply leaves capital R. Then we divide lowercase r squared by lowercase r cubed, which leaves lowercase r in the denominator. The intuition here is beautiful. All the complex geometry cancels out, proving that the surface area multiplier is simply the ratio of the large radius to the small radius. Now that we have seen the liver's bile in action, let us shift our focus to the pancreas. During a heavy meal, the pancreas acts as a massive fluid factory. It is responsible for manufacturing and secreting pancreatic juice, which is packed with the digestive enzymes needed to utilize all that newly created surface area we just calculated. This secretion is not just a tiny squirt. It is a continuous, steady flow that lasts throughout the active phase of intestinal digestion. Understanding the sheer volume of fluid produced helps us appreciate exactly how hard these associated glands work to process a single meal and why they are so vital to vertebrate survival. To understand the scale of this fluid production, we use a fundamental rate equation that connects volume, flow rate, and time. The formula is V equals Q times T. Conceptually, this is very similar to calculating how far a car travels if you know its speed and how long it has been driving. In this equation, the symbol V stands for the total volume of pancreatic juice secreted, measured in milliliters. The variable Q represents the volumetric flow rate, which is how fast the fluid is being produced every minute. Finally, the variable T represents the total time elapsed during the digestive process. If either the flow rate, Q, or the time, T, increases, the total volume, V, will increase proportionally, meaning the pancreas has to work even harder. Before we move on, let us see this with a concrete example. Suppose a vertebrate's pancreas secretes digestive juice at a steady flow rate of 2.5 milliliters per minute. The animal has just consumed a very large meal, and the active phase of digestion will last for 120 minutes. We want to calculate the total volume of pancreatic juice dumped into the alimentary canal. We choose our rate equation because we have a constant flow over a specific duration. We substitute our known flow rate of 2.5 and multiply it by our known time of 120 minutes. The minutes cancel out mathematically, leaving us with a final answer of 300 milliliters. Physically, this means the pancreas must manufacture nearly a third of a liter of digestive juices just to handle this single meal. Now that we have calculated their incredible output, let us look at how these glands are physically arranged. In this schematic diagram, you can see the central alimentary canal, specifically the stomach leading into the duodenum. Notice the massive liver positioned just above, colored in dark red. Tucked beneath the liver is the green gallbladder, which stores the bile. Follow the bile duct down, and you will see it joins with the pancreatic duct. The pancreas itself is the yellow, leaf-shaped organ nestled in the curve of the duodenum. This diagram beautifully illustrates how these external factories are physically tethered to the gut tube, perfectly positioned to empty their powerful chemical secretions directly into the path of the digesting food. We have covered a lot of ground today, so let us review our key takeaways. First, remember that the alimentary canal is just a hollow tube. It relies entirely on associated digestive glands, like the liver and pancreas, to act as vital chemical support systems. Second, we saw the mathematical power of emulsification, where bile shatters fat to exponentially increase the surface area, making enzyme action incredibly efficient. Finally, we learned that these glands evolved to help vertebrates extract massive amounts of energy from their environment, fueling larger and more active bodies. You now have a complete, masterful understanding of what these glands are, why they exist, and exactly how they function. Great job!